Today is Michel Dekking, and he is going to speak to us about combinatorics of Fibonacci and golden mean number representations.
Okay. Here's the abstract. Can anybody see the hand moving on the screen?
Yes, we can see it.
Okay. So how many mains are there to represent the numbers of powers of the golden mean? That's a sort of the central question. So it's base phi. So I replace the usual natural numbers by the golden mean, and then I see how can I write numbers as a sum of powers. And among these, the question is, what is the best way to do this? Because there's more than one way to do that. What is the relation with representing a number as a sum of Fibonacci numbers? So this is another kind of way to have a numeration system using only Fibonacci numbers instead of powers of an integer. I will give some answers to these things. Now, so I was asked to give a talk, and I said will be my title. And then one of the organizers mailed to me, we'll have fun hearing this again, which to me sounds a bit like I'm doing again the same story as 2 years ago. I gave a talk in 2020 also about base phi. But this is really very new, what I'm going to tell you. It's even so that the main theorem is only 2 days old. So this is all very recent. First, I give you some quick answers. So the first question was, how many ways are there to represent a number as a sum of powers of the golden mean? And the quick answer is infinitely many. Okay. Among these, what's the best way to do this? And the answer is you use the greedy algorithm, which is also known as the Bergman expansion. And the first part of my talk will sort of try to convince you that it is not the best way to do it. And in the second part of my talk, I will talk about the relation with, well, I will mainly talk about how many ways are there to represent a number as a sum of powers of the golden mean. But I will also talk about a relation with representing a number as a sum of Fibonacci numbers. And I will talk to you about something called the golden mean shift. I mean, because this is combinatorics on words, and this is an interesting operation on words, and I will be talking about that. Okay, here's base phi. So a base phi representation of a natural number n has this form. Here are the powers of the golden mean. There are coefficients. And actually, you can take arbitrary non-negative numbers as the coefficients. So phi in this whole talk will be 1 plus square root 5/2. It's the golden mean. And similarly to base 10 numbers, I will write them as positive digits and then a sort of decimal point, which will always be red, and then negative, the negative part. So R is a negative number. So L is the largest positive, and R is the smallest negative power of phi that occurs. But of course, in principle, you could also have infinite sums. When they exist, when the sums are finite, I write it like this. Now, about these infinitely many representations. So even if you just use digit AI, which are only 0 or 1, then there are still infinitely many finite length representations. So let me give you an example. So if you take phi to the power of 3 plus phi minus 1 plus phi minus 4, then this is equal to 5, which you might check. So 5 has this base phi representation 1000 dot 1001. But this one corresponds to phi to the minus 4. But well, we have this well-known relation for the golden mean, a sort of defining relation, phi squared equals phi plus 1, which also implies that phi minus 4 equals 5 minus 5, 5 minus 6. So you can replace this one by 2 ones. Well, the 1 by 0, and you let it follow by 2 ones, and you get another representation of 5. And you can continue with this game because you can replace this last one again by a 0 and 2 ones. And you have another representation. And obviously you can go on and on with this last one and have getting longer and longer negative parts. And so here you see what I mean by this golden mean shift. Oh, it's that you replace in this representation this a single 1, or in fact a sort of 1 0 0 by 0 1 1. That's what I call a golden mean shift. So now here is a special choice of a representation in base phi, and this is the choice made by George Bergman. So now I write DI to emphasize that I have only digits 0 or 1. And what you do is you do not allow a double 1. And now this time I will not write alpha n, but beta n, the beta for Bergman. And I have this representation. Oh. And it's a theorem that this is a nice way to do it, because if you make this a requirement, then suddenly you have only a unique representation. In particular, all these infinitely many things will not appear. And that has to do, of course, with the fact that there is no 1 1 allowed. Yeah, now I'm going to do something strange, because I'm going to present to you a completely new representation in base phi. And very presumptuously, I call this the canonical base phi representation. And at first sight, it's very strange, because again, I take digits, only digits 0 or 1. And again, I don't allow 2 consecutive digits to be both 1, except that I allow the specific digit C1 and C0 to be equal to 1 1, as soon as this is possible. And now I choose the letter gamma for associated to canonical, and the digits C. And so maybe you're sort of hesitating how you do this. So to obtain this representation, you first look at this a representation of n with C1, C0 equals 1, 1. And still the other double ones are forbidden. And if you don't succeed fitting this representation like that, then you simply, of course, you simply choose the old Bergman representation, because this is not possible. And there's again a theorem that this canonical representation of a number n is unique. Here I give you some examples. So here's n. If n is 2, you get 1, 0, 0, 1, and the canonical one is also like that. So let's see. So many of these beta ends and gamma ends are equal. So here at 7, you see first time you see here a C0, C1, which is equal to 1, 1. Oh. And so this is a 7 is a place where the Bergman is really very different from canonical. And then for 8, they are again the same. And for 9, they are the same. For 10, they are again different. Here you have a double 1. And so on. And so a very natural question is, so we see here that for 3 also, by the way, 3 is in Bergman, it's 100.01, and here it's 11.01. So we have 3, 7, and 10 where they are different. And actually, you can show that the numbers and where they are different is a very nice sequence. It's a BT sequence. It's integer part of 5 plus 2 times little n. And so if you take n equal to 1, you get 3. If you take n equal to 2, you get 7, etc. So there's a nice characterization of the spots where they differ. So how did I get to this so-called canonical representation? Yeah, this is a very strange story. Maybe kind of story that you have seen in some form sometimes yourself. That I was approached by a civil engineer. So he's not a mathematician; he's a civil engineer. And he is really fond of the golden ratio. And so he has written a paper, I guess never published, called the golden ratio, the origin of nature. That doesn't sound very nice. I mean, I would never write a paper like that. And he found my papers on the internet, and then he said, "Well, this Bergman representation is really not a good one. It's wrong. You have to make another representation." And he was sending me lots of pictures, like the one here, trying to explain to me why this was so. And of course, I thought, this is a nut. These things are really crazy. But I spent a little bit of time on it, and then I found out that it was not so crazy after all. Okay. So the question is, why is this not so crazy after all? Why does it deserve at all to be called canonical? Well, there's sort of 2 reasons for that. And this is the first reason. Look at the length of the representations. So if you are on base B, then you have length n in the intervals b to the n minus 1, b to the n minus 1. For example, you have in base 10, you have 2 digits between 10 and 99. Now for the base phi, the powers of b, well, in some sense, the powers of b are replaced by, of course, the powers of phi, the golden mean. But for this, the length, of course, of representation is an integer, and they are also associated to certain integers, the Lucas numbers. So they start with 2, then 1, and then the usual recurrence relation, which you also have for the Fibonacci numbers. And so the only difference is that you start not with 1, 1, but with 2, 1. This gives you the Lucas numbers. And this is an older result that what are the intervals where the expansion length of the Bergman anticipation is constant? Well, they are made out of intervals with these Lucas numbers. So these are the intervals lambda 2 and L2n, L2n plus 1, and L2n plus 1, which is similar, but just a little bit different from this. And you have length 4n plus 1 in these intervals and length 4n plus 4 in these intervals. So what are the intervals of constant expansion length for what I call the canonical representation? Well, they have length 2n plus 1 for n even and 2n plus 2 for n odd. And the intervals are what I call gamma n's. And they look definitely nicer because here I had to make two choices. Here I have only, I need only write down one thing for every n. Namely, it nicely starts at ln plus 1 and it ends at ln, at the next Lucas number. Okay, so let me explain again why it's so much nicer. So base B, you have these intervals Bn. Constant expansion length for the Bergman expansion, you have these intervals lambda 2 and lambda 2n plus 1. And for canonical, I have these gamma n's. And what's wrong with the lambda n if I compare them to the usual base B? Well, what's strange there is that the length of the even numbered intervals is in some sense too big, and the length of the odd intervals is too small. And the gamma n, they always have lengths ln minus 1, so which is much more like we have in the classical base B case. So that's my first reason to call this thing canonical. Now, second reason is the following, and here we look also at length, but now at length of vertical runs if you write down a table of the representations. So here's a table with n is 0, etc., 1, 2, etc. This is the binary representation. And then if you look in the columns, then of course, I mean, we all know this, you have a very regular structure. So in column 2, for example, you have double ones followed by double zeros, etc., all the time. And in general, in digit position I, you have only runs of 2 to the I ones and separated by runs of 2 to the I zeros. Now, for the Bergman expansion, there is no such regularity. If you look at the vertical runs, and I haven't made the table for you, but you have to believe me, that you see all kinds of lengths. Length 1, length 2, length 3, length 4, length 5, length 6, length 7. They are completely random in some sense. But for the canonical expansion, this is completely different. In the canonical base phi expansion of the only vertical runs of ones occur where the length is a Lucas number. And all Lucas numbers occur as a run length. More precisely, if you take this position I, then only runs of length L minus 1 occur for the positive I. But also for the negative I behaves remarkably nice, because there you have only runs of length L minus I when I is small equal to n, where I extend the Lucas numbers in the usual way also to the negative numbers. Okay, maybe I should take a little break here, because this was the first part of my lecture. So if there are any questions about this strange canonical expansion, then please ask them. Difficult, eh? These Zoom presentations. Okay, so I go to the second part, and that was the next question. So how many ways are there to represent a number as the sum of powers of the golden mean? Well, actually, there's not much is known about this question, but really a lot is known about a related question. So how many ways are there to represent a number as a sum of different Fibonacci numbers? And so in the audience, there's Jeff Shellett, who has also looked at this kind of thing. There's so many papers about them that you also see them in two names. You see them as minimal Fibonacci representations, but they're also known as Fibonacci partitions. And this indeed has a long history. It started in the 60s. It's a good paper by David Klarner, paper by Leonard Karlitz. And it goes on and on and on. So there's also a recent paper by Chow and Slattery, which I think is only available on arXiv. So these minimal Fibonacci representations, they are also known as Zeckendorf representations. So they are very similar to what we did with Bergman. So you write an n as a sum of Fibonacci numbers. You start at I equal 2 because I want them all to be different. So the F2 is equal to 1. So I have 1, but I don't want to have more, not the F0 and F1. So they always start at I equal 2. And you have the same, it's a greedy algorithm. You do not allow 1, 1. So there are no two consecutive Fibonacci numbers in there. And I write Zn, the Z for Zeckendorf of n is dl till d2. Example, the Zeckendorf expansion of 6 is 1001, since F5 is equal to 5 and F2 is equal to 1. Okay, here I have them next to each other. Here is Zeckendorf, here is Bergman, and Bergman looks much more complicated, and in some sense it is. Now, how many ways are there to represent n as a sum of Fibonacci numbers? And this is one of the oldest sequences in the online encyclopedia of integer sequences. So I write this as tfib, as there's only one way to write 0 as sum of Fibonacci numbers, only one way to write 1, one way to write 2, two ways to write 3, namely you can write 3, but you can also write 1, 2. Well, I'm sort of hesitating there. Well, let's look further later on to the sequence. So it looks quite complicated, and in some sense it is complicated. It has a sort of fractal structure, but the recursions were given by Neville Robbins, and in this recent paper by Chow and Slattery, they exploit this a little bit further. So, for example, let's look at Z8. So 8 is the 5th Fibonacci number, so it has this minimal representation. This is the Zeckendorf representation of 8, but there are other representations possible, because 8 is also equal to 5 plus 3. So I could write 1, 1, 0, 0, because this is the position of the 5th Fibonacci, the 4th Fibonacci, the 3rd, and the 2nd. So this is the reputation 5 plus 3, and this is the reputation 5 plus 1 plus 2. So the number of representations of 8 is equal to 3. So this is repeated here. And now I come back to this golden mean shift. So a little bit more formally, it's a map G here, which actually depends on N, on 0, 1 words, where if you have a word W1, WK, then at position, suppose that you had at the position n plus 1 or 1 and the next two are 0, then you replace the 1 by 0 and the 2 zeros both by 1. So the G of Z8 is the G of 10,000, and so it is this one. And then I can continue, I can take the G of this one, and then it's 1011. So in some sense, this is of course the word version of the defining equation for the Fibonacci numbers. And now, the sort of trivial but extremely useful remark is that it's also the word version of the equation for the powers of phi. We know that phi to the n is phi to the n minus 1 plus phi to the n minus 2. And if you have a Bergman representation, then you can do the same kind of thing. If you see a 1, 0, 0, you can replace it by 0, 1, 1, and the outcome will still be the same. Okay, so now I come back to this question of how many ways are there to write a number as powers, and we have seen that there are infinitely ways. Now, you have to do something to make it finite if you want to count. And there was a proposal by Ron Knott, an English mathematician, and you can find it in the online encyclopedia of integer sequences as a much more recent sequence. And it's called the number of ways not ending in 0, 1, 1 to write a number in base phi. And it is T kappa, and it looks like this. And yes, people get enthusiastic because they see the Fibonacci numbers here, 1, 2, 3, 5, 8. But then later on, it really gets a mess. So now Ron Knott has a lot of websites on these kind of things, and he also has a website where he presents to you a way to find all forms. So all forms base 5 forms of 2 are 1001 and 1.011. And so note that this is again a case of golden mean shift. You get this one by replacing this one here in position 1 by a 1 in position 0 and a 1 in position minus 1. So this is another representation of 2. And you can do the same for 3, and you can and for 4, and this is a sort of list which you can get from his website. Now, what I want to do is, I'm not completely happy with his proposal, because if you look, for example, for 3, he says all forms are, so it's this 100.01 and 11.01, and there's this one, 10.0001, but you cannot get this one from the other two by a golden mean shift, and they are really obtained in a different way. So what did he do? He took, so let's look at 4, so 101.01. And then what you do is, although in some sense you didn't allow it, you replace this one by 011. And so this you are not going to count. But the trick now is that you replace this one also by 011, and then you get something like this, which suddenly does not end in 011. So that's why he has put them here. Okay, so what I'm going to do is I remove all these, some people call this a double golden mean shift. And you have to jump over this one and then you get this one. And I remove this from the tables of knots, and then I get something which I call T phi, what I call the number of ways of representing a number in base phi, where I forbid 0, 1, 1 at the end. And so here you have these two 3s for 3 and 4, and they will now be replaced by 2, 1. So this is all these numbers, no, not all of them, some of these numbers get smaller, some of them stay the same. Okay, then I come to the theorem, which maybe looks a bit strange to you. So, and it looks strange to me also because I have this Zoom thing, which is sort of taking my view away on the top of the page. So it's a theorem which tells you how to count these base phi numbers. And at first sight, it looks a bit amazing. If you want to know the number of representations of n in a base phi not ending in 0, 1, 1, you can also take the number of representations of the Fibonacci numbers, but not taking at n, but at the number, let me see, at the number, the Fibonacci number with index minus Rn plus 2. So Rn is the length of the negative part of the base phi representation, and you multiply by n. So one of the things you should note is that, so this gives a way to compute this function T phi. And also it's nice that it is a subsequence of the numbers which you see in the representation, the counting sequence of the Fibonacci representations. Yeah, I have been told always that in a talk you should always give at least one proof. And let me do that now. And in some sense, it's amazing that I'm more or less capable of putting the proof on just one sheet. So let's look at the proof. So the starting point is that I take n here. I have a Bergman representation of n. So n looks as a sum from R to L di vt di. So Rn, I write for short, I write R for Rn. What I do is I multiply by phi to the minus R plus 2. Yeah, this formula here. So phi to the minus R plus 2 times n is now a sum, and where phi to the I has become phi to the I minus R plus 2. I have multiplied both sides by phi to the minus R plus 2. And now, then I like to call I minus R plus 2 J, and which I have done here. So the I becomes J plus R minus 2, and the sum runs now from J equal to L minus R plus 2, of course. And then I like to call these J plus R minus 2, like to call them E of J. That's all what I do in this last step. And well, I hope that everybody knows this equation, that you can express phi to the j nicely with the aid of Fibonacci numbers. Is phi to the j is f of j phi plus f of j minus 1. And so this every phi to this, so this power, phi to the minus r plus 2, that becomes phi minus r plus 2 phi plus f minus r plus 1. Just this equation for j equal minus r plus 2. And of course, I also do the same with the sum which I have over here. So all the phi to the j's become this. Yeah, but if you look at this, I mean, it looks a little bit with a lot of things, but it's just simply something of the form a phi plus b. And if I put this to the other side, you have a phi plus b equals 0. Now, a phi plus b is equal to 0 only if a is equal to 0. So I can take out everything which is in front of phi, which is phi minus r plus 2 times n. And here in front of phi, I have this sum ejfj. So this is the formula I get, which is a nice formula, because on this side, what do we recognize? I have Fibonacci numbers and I have EJs, and I have a sum starting at some j equal 2. So this is just a Fibonacci representation. And even more, because the original D's did not have a 1, 1. So the EJs will also not have a 1, 1. So this is just the Zeckendorf expansion, well, of this number here, of the number f minus r plus 2 times n. But the manipulations that the manipulations that I did here, I can do for any 0, 1 word of length L minus R plus 1. So I can, if I'm going to count above here, how many base 5 representations I have, I'm going to do this rule 1, 0, 0 equals 0, 0, 1 on these things. And then they are in one-to-one, and then I do exactly the same stamp, and then I get here also some well, actually the same sequence of zeros and 1. So I have a one-to-one correspondence between these two sequences. And so all the golden mean shifts that I can make with the D's correspond to golden mean shifts which I can make with the EJs. Well, but that does exactly mean that the number of representations is equal to the number of Fibonacci representations of this number, and that's what I have here on the left side. So that's the whole proof. Now, I told you that this theorem was only 2 days old, so maybe you have some hesitations about whether it is true. So I propose here a sort of a small independent check of this theorem. And at the same time, you can learn a little bit more about base phi numbers. So the Lucas numbers are extremely important for base phi. And one of the reasons is that you can express them very simply as with powers of the golden mean. You have the L2n is phi to the 2n plus phi to the minus 2n. And the L2n plus 1 is L2n plus L2n minus 1. So this you prove very easily by induction. And well, look at it. This means that the Bergman representation of L2n is a 1 followed by lots of zeros, and then it ends in a 1. at position minus 2n. And if you think about it, this representation is also simple. It looks very different. It's a lot of 0, 1 to the power n. Now, so you can read off what is the length of the negative part of L2n. It is 2n. Yeah, this is negative, so the R L2n is minus 2n. And the same on this side. Here also I have a length 2n. And it's also clear that the number of representations of L2n is 2n. Why? Because you can take this 1, and then you do a golden mean shift, and you get 0, 1, 1, and then you can again do a golden mean shift on the end, and so you can go on all the time. And you can do this 2n times. So this is there are 2n representations of L2n. Here it's completely different because there's no 1, 0, 0 anywhere. So there's only one representation of L2n plus 1. That's this one. Okay. Now now it seems that now I can apply a theorem count to these two numbers, the L2n and the L2n plus 1. And theorem count says that I have to take this number L2n, I have to multiply it by f minus r. So this is 2n and plus 2. And I do the same here. So I find for these numbers which are a product of a Fibonacci number and a Lucas number, I found this theorem gives me the exact number of representations. Now I already put here a question mark. Is this now new or not? Because we know that there are thousands of formulas relating Fibonacci's and Lucas numbers and so on. And indeed, so if you look in the online encyclopedia of integer sequences, you see there's a contribution by Miklos Christoph in the page on the Fibonacci numbers, and he says that a product of a Fibonacci number and a Lucas number can be written as a sum of two Fibonacci numbers. Well, actually, we are in this last case because we have an odd number. B is odd in our case, so we get the product is a difference. So let us apply this remark. And we get that f2n plus 2 times L2n plus 1 is the f of the sum, which is 4n plus 3, minus the f of the difference, which is 1, or f1, and f1 is equal to 1. So this is f4n plus 3 minus 1, this product. So actually, we don't have really an interesting new formula. Why? Because it's well known that if you take a Fibonacci number and you subtract 1, then you always get only one representation. So no new formula, but a check of my count formula. Okay, that was it. Thank you.
Oh, thank you very much, Michel. So during the talk, there were some questions that came in the chat. So I'm just going to read those.
Oh, I didn't put on the chat. Oh, yeah.
Oh, that's okay.
Yeah.
So Lepsheva has a question. It is known that we can't normalize to the Bergman representation with a one-way transducer, left to right, let's say. Is it the same for this canonical representation?
I'm afraid not. But it's an interesting question. My guess would be that you cannot.
Okay. Oh, sorry. Go ahead.
No, well, I just say it's worth looking at, but I did 0.0 on that.
All right. So Melody also asks, are the algorithms for addition, multiplication of integers somehow easier for the canonical representation?
No, well, they are very much the same. That doesn't make a big difference. If they were, I would certainly have mentioned them.
All right. And Pierre Arnoux asks, the Bergman representation, if I'm not mistaken, is the greedy one related to the multiplication by phi, the phi shift. Is there a similar dynamical system related to the canonical representation?
I don't understand this question completely. For Zeckendorf, you have something, you can look at it as a dynamical system. That's right, but I don't think you can for Bergman. Bergman also has, because if you want to look at a dynamical system, you sort of want to have shift invariance so that any word can occur at any position, which is true. Any factor can occur in any position, which is true for Fibonacci representation, but it's not true for Bergman. So in Bergman, you have quite some severe restrictions of words which can occur at, let's say, at position 2, but not at position 1. So I don't think this works. So, well, maybe Pierre can send me his question over the mail, and I will think about it.
Okay, yeah, Pierre says, okay, I had not understood that. Thank you. And Jean-Paul also had a question. You showed a table with Bergman versus decomposition in powers of phi. What about canonical versus powers of phi?
Bergman versus... let me see what he's referring to. Bergman versus powers of phi.
You maybe I'm mistaken, but you had a table where you can, yeah.
Oh yeah.
Zeckendorf, yeah. If you replace Bergman with canonical,
this is Fibonacci versus Bergman.
Yeah.
And you say Bergman versus
Fibonacci versus canonical.
Well, it looks very much the same because anyway, 62% of the time, the beta ends are equal to the gamma ends. Yeah. So so there's this rare BT sequence where they differ, which is 3, 7, 10, and then and so on. It doesn't give you anything interesting.
Okay. Now, my hope was it would be it might be simpler to compare ZN and the canonical one, because I mean, in case you see on your table that you have essentially most of the time you just add some sort of decimal part, so to say.
Yeah.
but not in the bad cases. And my sort of hope was that maybe with the canonical you would have some sort of uniformity, something uniform, and no, not.
No,
okay, it's not
no,
okay.
Absolutely not. I mean, I still think that the canonical expansion is a sort of is a strange idea. I think in our paper I put also some remarks about it, that it's clear that it's not something you would think of as a mathematician. Because in some sense it's very unnatural that you make this this exception for position 0 and position 1. And it's only a very big surprise that in some sense you get closer to base B, a natural number, with canonical than with Bergman. But I think all the other things which you would like to have from a base expansion, they are not nice.
Okay. Thank you, Michel.
Dan says that it's almost like you're gluing two one-sided shifts together at the origin.
No, I think that also is not true. I don't think you can make anything out of that. In some sense, also the negative and the positive part are not that different. So it's not a question of gluing. It's just the way it is.
All right. Does anyone else have any questions? All right. If not, thank you so much, Michel.
Okay. I would really like to